to our second lesson of the day. My name is Okuthe. We want to proceed with this topic called radioactivity. We have already looked at radiation detectors, so we want to move a step further and look at something called decay law. Decay law. And decay law, just like any other law, we are required to state it. And decay law states that the rate of disintegration at a given time is directly proportional to the number of nuclides present at that time. So meaning for decay process to take place, then it will depend on the number of nuclides that are present, the number of, or the mass of the radioactive sample present. Then it is also, or it will depend also on the time that will take for that disintegration process to take place. We move a step further and look at something called half-life. Half-life, I think, is a word that we have all met, even in chemistry. And half-life here is the time taken for half the number of nuclides initially present in a radioactive sample to decay. We can use half the number of nuclides, we can use half the mass of nuclides, or we can use the activity of the radioactive sample. So half the activity, half the mass, or half the number. So for example, when we have maybe 5 kg or 5 grams of a radioactive material. So if this radioactive material undergoes radioactive decay, then the time it will take for the mass to reduce to half, or half of it to decay, that means 25 gone, we are remaining 25 grams. Then the time taken for the mass now to remain 25, that time is what we call half-life, and we use the symbol T subscript, a half, to denote half-life. Yeah. If it is a number, for example, you are looking at the number of nuclides initially present. Probably there are 2 million present in the beginning. So time taken for this number to maybe become 1 million nuclides, that is also called half-life. So when defining half-life, we can use half the number, we can use half the mass, we can use half the activity of a radioactive initially present to decay. Now, when we want to determine the half-life of a radioactive substance, there are 3 major formulas that we use. The first formula is called decay series. Decay series. That implies now you look at the original mass or original number of nuclides initially present, then you reduce it half. For example, if the original number present was n naught, yeah, so for it reduced by half, it needs to become n naught over 2. N naught over 2 to reduce by half will be n naught over 4. N naught over 4 to reduce by half, or to decay by half, will be n naught over 8. So when we write it like that, that's what we call a decay series. So to move from this stage to that stage, from n naught to n naught over 2 is a half-life. From n naught over 2 to n naught over 4 is also a half-life. From n naught over 4 to n naught over 8 is also one half-life. So this half-life can be in seconds, it can be in minutes, it can be in days, it can be in years, and so on. So it is time. Yeah, so it can be in any of the units of time. The second method of determining the half-life of a substance is called the decay formula. Decay formula states that, as it is given there, n is the number of nuclides originally present, or the mass of nuclides initially present, is equal to n naught into a half in bracket power. T is the total time of decay, even if it is 5 years, then over t, this small t here is the half-life. They didn't indicate t half, but we just use it as given that formula, over t. So if maybe the half-life is 1 year and t is 5 years, therefore we just take 5 over 1, which will give us 5. So we raise half per 5 and simplify mathematically to get the half-life. T, or the mass that will be remaining after a certain period of time, or even the original mass, depending on what the question has given and what the question wants. Finally, the third method of determining half-life is called using a graph. When you plot a graph of number of radiations or number of nuclides present against time for various time intervals, then we get a graph that looks like that. This graph, when drawn, will not always touch the horizontal axis, the time axis. So it is a graph that will move in that manner without touching any of the axes, except the y-axis where it begins, the vertical axis. So, if the original number present is n, then the graph will start from n there. So, the time taken for now the mass to reduce from n to half n, that time, if we extend it, if we look at that number of nuclides, for example, if n was 100, then half n will be 50. So we come at 50, check. At 50, what is the time? So the time that will be recorded there will give us the half-life. Similarly, sometimes maybe a graph is given that is not touching this axis, but you are given a hanging graph where you can read any number of nuclides present or mass of the nuclides initially present. So you can even take it at half n. So you record the time at half n. Then for half n reduced by half, meaning it will become a quarter n. Then you also check the time it takes to have a quarter n. Then the difference between these two times, will give us the half-life. Similarly, you may also, so it means the graph can be taken at any point. It doesn't necessarily mean that it must be taken from the beginning here. It will depend on how the graph is drawn. If the graph is able to give you any value, then you take any value there, then get half of it, get the difference between those two times, will give you the half-life. Let us now look at an example that involves background radiation and requires us to work out half-life. The question reads, the activity of a radioactive element when measured using a GM tube is found to be 63 counts per minute. Given that the background radiation is 8 counts per minute, determine the first one, the actual activity of the radioactive element. So it was found to be 63. But then there is background radiation, and remember we said actual or correct activity is normally the recorded one, you subtract the background radiation. So the one given here is 63, that's what's recorded. Background radiation is 8, so the difference gives us 55. So 55 is actually what is the actual activity of the radioactive element. Part B, the half-life of the element if the activity dropped from 128 counts per minute to 23 counts per minute in 6 hours. So, even these count rate given here have background in them. So to get the correct one to use, like initial activity, which we represent with N0, will be 128 minus the background radiation, which is 8. So 128 minus 8 gives us 120. Final activity is given here as 23. So because it has background radiation in it, the correct one should now be 23 minus the background radiation, which is 15. So these are the correct activities to use in our calculation. Time given there is 6 hours, so they want the half-life. So we can do this using two methods we've talked about, that is the decay series. So decay series, we start from 120. So for 120 to reduce by half, it means to become 60. So time taken to move from 120 to 60 is 1 half-life. Then 60 to reduce by half, it will become 30. So for it to, or the time taken to reach that 30 is 1 half-life. Then for 30 reduced by half, it will become 15. 15, remember, is our final activity. So we move from 120 all the way to 15. We don't go beyond 15 because our question talks about 120 as the initial and 15 as the final. So we can see that to move from 120 to 15, we have 1, 2, 3 half-lives. So 3 half-lives take 6 hours. Therefore, 1 half-life will be 6 divided by 3, which is 2 hours. We can equally use the decay formula. And decay formula, we said n is equal to n naught into a half power t over t half. N already we have there as 15, the final. N naught is the initial, we have there as 120. In bracket into a half power x. I'm using x to represent this part. 6, t is 6, then half-life is what we are looking for. So we solve for x first. So we simplify. We divide both sides by 15. We'll get 15 over 120 is 1 over 8. Half power x will just be half power x. Then we write this in a simplified form. We'll have half power x equal to half power 3, so that x will be 3. But since x is 6 over half-life, therefore 6 over half-life is equal to 3, and 1 half-life will be 2 hours. Thank you very much for being attentive during the lesson. Welcome.